In this sequence, we will cover damped second-order systems. So before we begin, I wanted to caution you that there's going to be a lot of math here, a lot of theory, okay, that I will take you through. I want you to stay with me. It's going to be very grubby and very grungy, but hang in there. It turns out that all of this theory and math that you will see in this sequence is largely for your cultural background, all right? You really won't be responsible for it in your tests and homeworks and so on. However, it's really important to know where certain things come from. So despite all the math and grubbiness, there will be one point in the lecture where you will hear the word or words characteristic equation. I want you to really perk up and pay attention at that point. The amazing fact will be that despite all the math, despite all the theory, despite all the differential equations, what we really need for circuits analysis is something extremely simple. Okay, and towards the end of the sequence, I will show you that one simple little thing that you need to know, and from that you will be able to more or less predict the entire behavior of these second-order circuits simply by understanding the characteristic equation, okay, and how that comes about. Okay, so hang in there. Let's get started with this section, and watch out for when we get to characteristic equations. From there, things will become extremely simple. Now, let me start with a quick review. In the last sequence, we did the example of a pair of inverters that looked like this. So this was node A, this was B, and this was C. And I showed you the following equivalent circuit for those inverters. And we said that if I applied voltage A at the input of the first inverter, and if I try to speed up node B by turning on switch S, and have a small resistor 50 ohms in parallel with the 2 kilo ohms in order to speed up my circuit, I said that what I observed was a waveform that looked oscillatory like this. And all that we have seen so far does not quite prepare us for this. We did look at LC circuits in the last sequence, and we saw some sinusoidal behavior. Okay, but we didn't quite see this kind of decaying sinusoidal behavior, and we will see why that is so in today's sequence. Now, in the last sequence, we also learned that when you have a loop like this, there is inductance associated with the loop, and we model that as a little inductance L. And the relevant circuit, okay, to analyze, to understand this kind of behavior was given by this. So here was my 5 volt supply, and here's my 2 kilo ohm or 50 ohm resistors, depending on, it's actually 2 kilo ohm in parallel with 50 ohm resistance. And here was my inductance L, and then I had a capacitance CGS here. Okay, and this was my node B, and this is where I picked my ground node. So this was a second order system. In the last sequence, we analyzed a simpler form of a second order system without the resistance. Okay, just a straightforward LC circuit. Now what we're trying to do is trying to understand where this kind of oscillatory behavior comes from and try to understand the dynamics of that behavior. Okay, and if you want to go and take a look at the demo I showed you for a pair of inverters in the last sequence, you can go back and review that. All right, so the last lecture we started by analyzing the simpler LC circuit without the resistance. And here is what we studied: voltage VI, inductance L, and a capacitance C. Capacitance C, inductance L, and node with voltage V, and this was my current I. So we said let's start by analyzing that, and in doing so, the first step we wrote the differential equation that governed the dynamics of that system. We wrote the equation for node V, the node with the voltage V, and that was given by d squared V by dt squared. It was a second order differential equation. 1 by LC V equals 1 by LC VI. And we said, let's go ahead and solve this for input that looked like this. And this was T, and we said, let's take a step. Voltage, this is for voltage VI, take a step that goes from 0 to capital VI. Okay, so this input could be represented as VI U of T, where U of T is my unit step. Now the reason this input voltage, capital VI, reasonably modeled the behavior of the second order circuit was that, notice when the MOSFET turned, when the